So I want to start by thanking all of you for coming to this morning Kubernetes session. My name is Marek Grabowski. I am software engineer from Google Warsaw office, working on Kubernetes for since the beginning of the year, so half of the life of the project. Before joining the Kubernetes team, I was working on our internal infrastructure. So I moved from the systems to systems, from the closed one to the open source one. And I want to share with you some details about how we approach managing containers and how we think it should be done. So what I'm going to tell you is, first I'll just quickly remind all of you how we can share machines in different ways between apps. Then I'll tell you briefly what the containers are and how they work and why we think this is the correct thing to use when sharing machines. I will also briefly speak about Docker, which is a big thing in containers right now. And then we'll move to the main part of my presentation, which is introduction to Kubernetes, all the abstractions and all the ideas we want to share with all of you. I hope that by the end of this presentation, even if some of you just decide don't want to try with Kubernetes or just don't like our ideas, at least they will have something to think about. So please try to understand why we chose to do things the way we chose to do them. Because all of them, well, we have some reasons. We do have some experience with running containers. And some of us still have nightmares about some things we saw. So once again, welcome, and let's start, because I think we finally have everyone here. Whoa, it's class full. Okay, so the very, very old way of sharing machines, physical machines, is to just run multiple apps on the same physical machine, which is standing somewhere in the data center. So everyone can SSH to a machine, start some application, and it will be running, hopefully. I say only hopefully because if a lot of people will do this thing, it's quite possible that there will be some port collisions, some application will use all the CPU and there will be no resources left for the other apps. If anyone uses two applications use the same DLL and one will try to upgrade this version of this library, second one can break, all of really bad things can happen if people do this way. It is a pain to manage clusters of cluster running applications using this way of sharing, even though it was done for quite some time. Just because industry was using tens of machines, so it's possible to actually manage them by hand. But after some time, people realized that it's probably not the best way to share machines, so they introduced the virtual machines, which means we virtualize hardware, run in a completely new operating system on top of it. So we had a kernel, all the kernel structures inside each of the virtual machine, and run hopefully single app in each virtual machine, which certainly solved the isolation problem. So we can set the amount of resources each VM uses, and then no other VM can no other app can use the resources assigned to the given VM. The problem with the VMs is that they are kind of expensive. It gets better right now, but still, there's a huge overhead when starting them up. It takes a few seconds at least. There is some overhead on the I/O operations, especially the small ones, and there's some memory overhead for all the kernel structures. though it gets better with time. So maybe in future, virtual machines will be a very good way of sharing machines, but it's not. We're not there yet. A small problem with them is that how the people were using them. They were just using virtual machines or normal machines. So and they really cared about particular instance. So there was one single VM that were running, whatever, some database or something. And then it turned out that we need to upgrade the kernel on the machine on which this VM is running. And now we have a problem because we need to somehow move this VM to some other place, which can be a pain. So few years back, a new idea appeared, which means that we can use containers to run VMs. The containers is not only the way of isolating applications, but also way of how we think about them and how we develop them. So containers, from a bird's eye view, is just some small process which is isolated from other processes running on the same machine. In addition to this isolation, we want the processes, applications running in containers to be static binaries. So we don't want any external dependencies. We don't want to use any DLLs from outside these containers. We just want everything to fit in this isolated container, which means that we upgrading one of them will not ever break anything else. It can only break the container we are upgrading, but all the other containers will keep running because there's no shared libraries, no shared anything, except kernel. Kernel upgrade is still a problem. I will tell you briefly how you should design applications to mitigate the problem with kernel upgrade, but it will come in a few minutes. Okay, so I already discussed it a bit. One can think about containers are really lightweight VMs that, instead of giving hardware level virtualization, gives us software level, OS virtualization, that gives you the limited view of the operating system, all the system you're running in, but the hardware is the same. So it just isolates the viewpoint of the process, resources, namespaces, everything. And it's nothing magical. It's actually everything is available in Linux kernel. All the APIs are already there. Probably at least some of you heard or used some of them or even all of them. They were appearing over the last 10 years or something, completely they were never designed to work as a single thing, but they were people were adding different things they need. For example, the C groups, which I don't know how many of you know what the C group is. Okay, not a lot of you. So C group is you can wrap a process in a C group and assign some resources to it. So basically, you can tell that this process can use only half of the CPU worth of shares, or only 3 gigs of memory. And the C group will take care of not allowing this process to use anything else. It will never use more than this amount of CPU and this amount of memory, disk I/O, whatever. Second things are namespaces. So who used namespaces? Okay, I see we have some of guys, and the rest probably are devs. So namespaces basically limit the view of the system that is available to the process. So for example, the most important example for this is that you can, for example, split the network interfaces. So you will have virtualized or separate network interfaces for each process, so they won't collide with each other. Other things are capabilities. So they limit what users can do. So if the given user can kill some process or mount something somewhere or whatever. And truths. Truths truths is a way of specifying a view of the file system for the process. So you can just tell the make the process to see only some part of your whole file system. This way you can, for example, like split the root kind of, the things that different processes consider as a root directory. So all those things are already there for quite some time. And the problem with them is that it's kind of hard to configure all of them by hand. Like, they're not really straightforward to use, but if you were able to just configure them correctly and run a process inside of the C groups, namespaces, capabilities, and so on, then, what you will get will be basically a container. The good thing is that if, whether half of you will try to do this, they will eventually end up with pretty much the same setup. Which means that it's kind of easy, at least it's possible to make it automatic. So you will, to make a system which, does all these C group namespace, whatever, things for you. So that's what the Docker did, actually. Plus, they added some other things. So Docker can mean multiple things. For me here, it will basically mean the implementation of container idea plus ecosystem. So what they did is they created a software that wraps the binaries inside something that's called Docker container, which contains some metadata like how to mount additional volumes to the process which is wrapped. They also developed a repository for images, so anyone can build a Docker image, upload it to the Docker repository, and then in any other place in the world download this image and run it. It is also a Docker daemon, which runs when you start a Docker, it runs as a root and manages the container that is running on the machine. So they created all those things, and it became became really popular pretty quickly, and the interest in Docker is still growing because it's so easy to use. I don't know how many of you use Docker ever? Okay, that's a fair number. So you probably can agree that it's really simple to use. It's just Docker run whatever and it runs. And it does all this isolation for you. This is the Google Trends thingy for Docker. As a point of reference, I can tell you that right now it's roughly the same level of number of queries as, for example, Django. Which is the difference is that the interest in Django is going down, interest in Docker goes up, so they will probably intersect each other pretty soon. So this is really successful startup which tries to change the world and tries to change the way people think about running their software. But if you want to use these containers to run things in your cluster, you probably don't have a single container running there. That's not very interesting. Then you can really run it on a machine, SSH on it. So you probably want to have multiple containers running there, especially when we as community, at least I think that we are currently moving towards the microservice architecture. So we have a lot of services, loads of containers, and they just multiply each other a lot. When the current architecture of the systems I saw in the past conference, the number of services grows really fast. So if you want to run your service on the cluster, you probably need some other tools except Docker to do this. You need something that will help you with scheduling. So I have this container, please run it somewhere. I don't want to by hand telling that I want to run this on the machine number 1, 5, and 7, because when I have thousands of those services, I will just do only this the whole day. We need something that manages the life cycle of containers. So like if the container dies and I know that it should be running, something just notice it and restart it. I don't want to like check if container is alive over and over again. If you have multiple containers, and especially if you have automated scheduling, you need some discovery mechanism. So like this container is running somewhere, I want to connect to it. Like, how do I do this? Like, it's like if I schedule them by hand, I can just like write it down on a piece of paper somewhere, and then this container has this IP and try to do this. But if this container die, the data is well obsolete. You need to upgrade it, update it, and it's really, really hard. You also need some monitoring. So you want to know how much resources your containers are using across the cluster, like all the instances of some distributed database, how much memory or CPU it's using right now. Some authentication mechanism, so like to limit what users can do with the containers running and which user can do what. You need also some way to aggregate running containers. For example, I have running some front-end services, some back-end services, some database, and I want to be able to say that those containers are just like all the instances of the distributed database. Like those are the front-ends, those are the back-ends, those are the whatever. Need some mechanism for this. You also need some way of scaling things. Like if it's it turns out that I have two little containers, like I need to put more of the instances of the distributed database, then I need to be able to scale them, like add 2 more instances and make them work together again, like as a bigger distributed database, and so on and so on. There's a lot of things that needs to be done, except the single Docker container, to make it actually useful for people running clusters. And what we want to do, but lucky for, well, all of us, we were doing it for quite some time. Like, I don't know how many of you read our Borg paper, which appeared like pretty recently. This is a system, the description of the system that we have like for over 10 years, and what it does, it basically manages containers for over 10 years, and does all those things for us, like the things I mentioned in the previous slide. So it does the scheduling, does monitoring, does like a lot of other stuff. And we really like containers. Everything is a container in our internal infrastructure. Like if you ever used Gmail, all of the front-end, back-ends, whatever runs in containers. Web search, I don't know if any of you heard about a web search, but it still also runs in the containers. Google Maps, all our MapReduce jobs, our file system daemons, even in our compute engine, when we sell VMs, those VMs run in containers, which may not make sense for the performance reason, but like it makes managing them, like running them, so much easier because we have all those toolings around containers that no one even cares about running them on a bare metal. We package them in containers and run them because it makes a way smaller overhead for the operation people. And we really launch a lot of them. Like the rough estimate is 2 billion per week, which, to make the math for you, is 3,000 per second. So like it's probably like over 1 million since I started this talk, so that the numbers speak for themselves. They're obviously not in a single data center, so there's across the data centers, but well, we do not have whatever 1,000 data centers, so that's still a lot on the single one. Seeing this need for the container orchestration system that will help you with managing clusters, and having all this expertise, we decided to launch Kubernetes project. It was, well, announced a year ago on the DockerCon, which is roughly exactly a year ago, which is a system open source system that, well, in the future, will help you in all those things you need to run the cluster easily. So we'll do scheduling, monitoring, and so on and so on. Currently, it uses Docker as the container engine. And we are starting to implement the Rocket support. So Rocket is the CoreOS alternative to Docker. Docker was turned to be like a huge juggernaut that takes whatever they can. So someone launched an fully open source version, which is Rocket. To tell the truth, I think that Docker, like 2 days back, actually also turned like full open source on the DockerCon, because they saw that this problem that people, well, don't like any closed solutions. So the things change right now, like very this moment. We want the Kubernetes to be able to run anywhere, like literally anywhere. Obviously in our cloud platform, but also on Amazon, Microsoft, on your, well, even in bare metal, like you have in your basements or wherever. So you can use Vagrant to run Kubernetes. And that's like the system itself, but the most important thing we want to do with this project is to share our experience, to tell you which things work and which things don't work, even though if they seem to work at the beginning. That we know like how things change when you add the scale. So when some things may seem reasonable when you run like whatever 10 machines or 100 machines or 1,000 machines, well, 1,000 maybe not, but 100 machines, it still may be doable. But when you turn like few hundred or 1,000, things go sour. And we know where this dangerous lie and want to share with the open source community so that you don't make the mistakes we did in the past. These are design principles we had when designing Kubernetes. This is probably the most important slide in this whole talk. Some of the points are more important, some of them are less important. The first thing you should know about managing large clusters is that you don't want to be imperative. You don't want to tell the system exactly what to do. Like when you have a lot of machines, it's just impossible. So what you want to do actually is to tell system what the state you want from the system. For example, I want to have like 5 instances of this particular container running, and that's it. And let the system figure out how to do it. You really don't want to have anything imperative there, because like it really goes really bad really quickly. So to have this kind of system, declarative system, what we implemented in Kubernetes is our controllers, which runs the control loops, which basically means that we have services that observe the current state of the system. So like queries the whatever database we use to see what is the current state, what is running, what is not running, what nodes are healthy, which nodes are not. Also take the user's intent, so like how many instances of particular container needs to be run, and like tries to make the current reality a bit closer to the desired reality. And that makes a small step and then repeats until it reaches its goal. This is also the next one seems to be trivial. Like obviously, like simple components are better than complex components. But like when writing a system that manages cluster, which is complex task, it's really easy to add a bit more, like slightly more responsibility to one component, which in turn will really, really quickly grow. So one needs to be really careful when limiting responsibilities of particular components. So that's why and how we wrote our controllers, which actually each controller have really small responsibility. It looks at really specific thing in the cluster and tries to really change and really small things. There's not a controller which tries to do everything, like add instances, remove nodes, like to manage like network or whatever. So, but we have one controller for everything that's important. All modularity, which should be clear. Legacy compatible. That's probably most important for for us or for users. That is, we don't want anyone to have to change his or her app to run on Kubernetes. You should be able to take any container you have, any Docker container you have, Rocket container, whatever, and just run it. You don't need, you shouldn't be required to change it in any way. And this actually works right now. So if you have any Docker container, you can just start it on Kubernetes and it will just go. We believe that, Docker now believes this as well, so it's not important right now as it was like a week ago. But we believe that in open standards, we don't want to have any closed parts in our project. So everything is in GitHub. Everyone can just take whatever he or she wants from it and then use it. And we use also like the well-known standards like REST APIs, JSON as a data format. We also, like, this is thing that sadly in our internal system was an afterthought when designing it. So like first when you want to write the system that manages container, you care mostly about like CPU and memory. That's nice, but like if you don't think about network from the start and you will need to add it later, it will be a nightmare. Really a nightmare. I will tell you how we deal with the network in Kubernetes, because I think it's a really nice idea. So that this will come in the future. And like the thing that it's probably most important as a changing mindset of people is that the cattle are better than pets. A lot of people we talk to tend to treat their VMs right now or containers as pets. Like what to do when the pet is healthy and the cattle and the sheep is healthy, they just live and eat and sleep and whatever. So they're kind of the same. But the difference is what happens if both of them get sick, like any of them get sick. So if a pet gets sick, what you do? You just take it to the vet. The vet tries to some injections, basically tries to make the pet better. You take it home, see if it gets better. If not, then you take the vet again and repeat until the pet gets better. In cattle, it's not the case. With the cattle, we have a sheep which gets sick. You take the sheep to the vet. Vet tries to make the sheep better. If it cannot, for some reason, it's a serious illness or something, you just kill the sheep and buy another one. You really don't care about the sheep number 142. We need to change the mindset of the operations people that VMs and containers are not pets, they are cattle. Each and everyone should be able to die, and you should not care about it. Like you can spin up a new one and it will just take over the responsibilities of the one that was just killed. This mindset probably changes the most from all the things I am talking about. This mindset allows you to actually stress less about running clusters, because everything can die. I cannot do anything about it. It will die. I'll start a new one and it will just work. So if you design your system to work like this, it will be much easier to manage. Much easier to manage. So modularity, that's clear. All of the things we wrote, the moving parts, are interchangeable. If you want, you can write your own, plug it in, plug out the things that we wrote, plug in what you want, and it will just work. Loads of things, as I said, all moving parts. Replication controller, which is like the controller that manages number of replication, number of instances of containers. Scheduler, which manages scheduling. Everything that actually does something can be taken out and replaced with something else, as long as it implements correct APIs. So on a high level, this is how our design looks like. Those are we probably should be right now should be clear that we kind of microservice architecture with the API server as like the center part. The API server is really stupid component that pretty much everything that it does is just writes things to the database and reads things from the database. As a database of choice, we use etcd, which is kind of key value store, not a database, but still store some data. We have like the kind of master components, which is not a formal name, but it's just like master because it manages all the slaves. Which run schedulers, controller managers, which manages all the controllers. And at each and every node, we have two daemons. Kubelet, which is our daemon that monitors the health of the nodes, starts the containers, monitors them, and basically does all the housekeeping on the node. And the service proxy, which is also called kube proxy, which is our network. It's from a network stack. Why etcd? This is another interesting thing. These are some things that shouldn't be very confusing. It has optimistic concurrency, it's open source, and written in Go, which is important for us because we are also written in Go. It has a HTTP API, but the most important feature of etcd is that it has a watch kind of streaming RPCs. How many of you know what the watch is? Okay, no, yeah, so that I was, because we use watch for quite some time internally, so it was kind of surprised on the previous conference that people don't use watch. Watch is normally when you have an RPC, you just send a request and get a response, and that's it. When watch is a streaming RPC, which means that it's not that way. You just send a request and then are reading responses, multiple responses. What it does is actually sends you deltas of the state of the system. So basically you send I want to be updated on if something of this kind changes. And then if in the database, for example, some API object changes, you will get the watch. Well, the watch will send you the information that this particular things change and how it changed and what changed. So this thing, in a sense, allows you to cheaply implement something in between pull and push interface. Oh, sorry. Okay. So the best way to explain this is to actually use an example. So this is a simple scheduling walkthrough for our system. So let's say user tries to run a container with image foobar requiring 1 CPU and 3.4 gigs of memory. So it tries the request with the empty host. What now happens? Scheduler watches for all the containers that appear and have empty host. So it watches for it, which means that API server will send the or push actually the information that this actually appeared in the database to the scheduler. Scheduler will then process it and figure out which host to run, chooses some kubelets and write it to the API server. Kubelets watches again for all changes in all containers that have it as set as host. So it's a kubelet XXX, so it's just gets an information that, hey, this new container appeared and it has assigned kubelet XXX. So the API server pushes it to kubelet. Kubelet starts a container foobar and reports the status, writes the status to the API server. And now user, if interested in the status of the foobar container, can read the status, so it will have all the interesting information, like when it started, if it's ready to serve, like what the image is running, on which node is running, like all this stuff that you can be possibly interested in. So on the high level, we want users, so developers, not to care about nodes, like all the things that your applications run onto you. What developers should care about is to just write something that runs, tells the master, please run it, and forget about it. Just fire and forget. Please run it somewhere. The master will take care of running it somewhere and allow you to use it however you want. So users should be isolated from all those like multiple hundreds of machines. Now I want to dive a bit deeper into the Kubernetes abstractions we use, and actually I will tell you, I will give you some insights on why we think some of them are better than like the kind of intuitive ones. For example, one would think that container should be a base unit in the system like this, right? Like we are running containers, so probably like container that should schedule containers. But that's not really the case. It turns out, like that our experience shows that people very often need to run multiple containers side by side. Not a single one, but for example, two, like 5-puller and web server, like in a really close, they need to be exactly on the same machine. Like one is just read some data out, second one serve the data, or some service and log saver, log dumper. So some service that does something, and another small container that just writes the log to some kind of persistent storage. And those kinds of containers obviously have to run on the same machine. There's no point of running log saver in the other machine that it up. That it should be up that produces logs. They need to be on the single machine. So we actually think that the good definition of this smallest unit is a pod, which is like kind of defined of a small group of tightly coupled containers. So pod is a group of containers and they really have to run on the single machine. So there's no point of running them separately. This also is a place where we kind of differ with Docker. We don't believe that isolating network in containers is really important. We believe that pod is a good like unit for container for network namespace. So all of the containers inside a pod share the same IP, share the same network. They are communicating. They communicate each other on a local host. I will also tell you a bit more about it in the future. And again, cats versus battle. We should expect the pods to die repeatedly. So if you will ever design any kind of cluster management system, please do not think about like running really single processes. Like processes needs to be coupled. Like internally from the start we had like a single process or container as a unit. Then we need to build infrastructure around it to actually be able to do things like this. This should be really an item for scheduler placement and everything. So now the networking. Docker, by default, you can change this behavior because like we are using Docker. By default, creates a local virtual network on each machine. So like containers on a single node actually can communicate between each other like using the IP addresses. But if you're going between the nodes, you actually go through NAT, which adds some overhead. We don't think that's a good way to go. Well, because it makes managing cluster harder. You have a NAT and you need to care about it. So we believe that each container, each pod actually, has to have an IP which is routable. So you should be able to actually resolve the IP address of every individual pod. So it can be reached without a NAT. Luckily, there's a lot of solutions out there that helps you with it, like Open vSwitch, Flannel, whatever. This also helps you with additional very important thing, that you do not need to care about port numbers. Because another natural way to go is to just use host ports, host IP address, host network interface. But then you will really need to care about port numbers, because you cannot like open port 80 two times. So it is also like our experience that at first we did not care about ports and use host ports. And then we had to build something on top of it to actually like allow, like you need to write, like what you can do is basically either use DNS, which has its problems, which I'll discuss a bit later, or have some another like discovery mechanism that like this particular, that maps like pods to the pairs of IP and port, and then you assign random ports and disallow people to actually specify ports and use like static ones, which is also bad, because like if you want to use open source software, there's sometimes just hardcore port and then you're done. So what we want to have is to a system and a network when each pod has its own ports or own IP, which means that like you also still need to consider port collisions, but inside a pod. And like I never seen a pod with more than 3 containers, and like managing 3 containers is not very hard. Ports on 3 containers is not very hard, which makes it's way easier. So now the slight problem appears how one can discover such pods. Well, first idea might be to use like DNS, like everyone uses the DNS. The problem with DNS is that all the implementations I know of actually cache the results, and our pods die, which will make the cache just unreliable. You cannot cache the results here. You will get lots of false positives. So what we did, we introduced a like higher level concept, which is a service. Service is just a, from user perspective, it's just a static IP and port pair, which serves as the entry point to all the pods below the service. So the service manages like a set of pods, us as an entry point to them, plus as a load balancer. So it actually load balances the traffic between the pods. From user's perspective, it's really simple. You just like get an IP and port, just contact it if you want to contact this particular set of pods, and you're done. We also have a session affinity supported, so if one really needs a session, then use it. But like we believe that stateless pods are better. How it is implemented is kind of interesting, because we have like as I said, a queue proxy, the service proxy, on each node, which has a knowledge of every service in the cluster and every pod in and pods in each and every service in the cluster. So it's some data, quite a lot of data. And then, like when someone asks the queue proxy, and how can I get the pod from this particular set, then it just like run robinson, randomly, or whatever your load balancing algorithm is, just chooses one of them and then gives you the IP address. But so that's simple, but you also need to get to this queue proxy. So what we done is to configure IP tables in each and every node, that if someone tries to contact this virtual stable IP and port, it will just like pre-route it to the queue proxy on the local host. So there's like locally there's no overhead, but if you want to have like so the local is no overhead. Basically, what it does is just like reroutes it all the traffic through this small queue proxy, which runs on the same machine that you are running. So that's nice. Another concept we have, which should be really clear for pretty much everyone, are volumes. Like you can mount anything you want, anywhere you want inside the containers. You can define a volume on pretty much any imaginable kind. For example, you can have some empty directory, which for the pod, which means that containers in the pod will share them, so we can communicate through the local file system. And this directory will die when the pod will die, so it's ephemeral. You can also mount some persistent disk, like our DC persistent disk, Elastic Block Store for AWS, like whatever you want. And that they will survive the pod failure. So it's persistent, so like whatever you write, you will be able to read again. Another thing that we learned the hard way is that you really need to allow users to attach arbitrary metadata to the objects. Like if you don't allow them explicitly, they will figure out the way to do it. Like they will use names. Like you will end up with names like 1,000 characters long, and you will need to parse. Then the user will try to parse the names and then understand it's a front end, back end, or whatever. And it will be painful for users and you. So just allow them to add arbitrary metadata to all the objects, and it will make everyone's life much easier. So what we did, we used labels. Label as a key value pair, like everything, which is used to, in a sense, like, well, just to identify like some sets of objects. For example, here we have 3 pods, all from application Nifty, 2 of them in development phase, 2 of them in the test phase, 2 of them as well front-end pods, 2 of them back-end pods. So like you can attach this kind of metadata to it, and then you can run selectors on them. So selector is just a query on these labels, on this metadata. So what you do is you just take a set of objects, apply the selector, and get another set of objects that matches this selector. It's pretty easy. So for example, like if you want the all pods from app Nifty, you get all of them. If you want from app Nifty and roll frontend, you get the left pair, app Nifty and phase test, you get the bottom 2. It's really simple and really powerful and extremely useful. Because like how we use it heavily for exactly for controllers and schedulers and everything. So like the controller is the moving part of the system that actually observes the state of the system, tries to check the desired state of the system and tries to act on it. What is nice about our implementation is that we don't have any internal APIs. We have only external public APIs, so anyone can just read APIs and write their own controller if they want. That's an example. So we have like controllers for pretty much everything. Replication controller, which I already mentioned. Node controller, which manages nodes, which means machines. Endpoint controller, I think it's called service control right now, which is kind of manages network. And just like goes in this loop and tries to fix the current state of the system. What is important is that we want them to be, well, kind of independent. So like we use these labels to specify like what's interesting for the particular controller. For example, we have a replication controller that well, basically makes sure that the number of replicas running is the number of replicas that should be running of particular container pod. We use labels to specify like this controller should take care of container pods matching this selector. So like it just selects the from all the pods, the ones matching the selector, and make sure that there's enough of those pods running. So this is a simple example. Assume that like we have 4 nodes, we want 4 instances of pod running, and well, as you can see at this example, there are 4 of them running. But at some point, something will go sour, and one of the nodes will die. You can't know. It can be a network failure, which will resolve itself. Like in a few minutes, or it can be earthquake in the data center and the machine is destroyed. So you can't know what's possibly happened. So like the replication controller observes that, well, it can only see 3 pods running right now. So what it will do, it will just schedule a new one. Like as I said, the pods are cattle. Like if one dies, like just buy another one and it should work. But if it turned out that that was a temporary network failure, then and the node will reconnect, then the replication controller will see that it wants to have 4 replicas running and have 5, which means that it will just randomly pick one and kill. Again, it's a cattle. You shouldn't care about any particular instance. Like any of those instances should be able to die with the same result. Okay, so now to wrap things up, as for modularity and using open source software, we use a lot of stuff that's out there to do pretty much all the things that we are not caring about. So for example, we use CAdvisor, InfluxDB, Hipster for cluster monitoring, FluentD, Elasticsearch, Kibana for logging, SkyDNS as our internal DNS system. So if you want another monitoring, just pick whatever stack you want and use it. It's really that simple. Now the short status update. First of all, I think this night we published the release candidate for the 1.0 Kubernetes system, which is bound to be released on July 21st. www.kuberneteslaunch.com is Oregon if some of you want to go. What this release will handle will be stable API, so we won't make any non-backward compatible changes from now on. It can efficiently manage around 100 of nodes and 30 pods per node, which means you can run around 3,000 cluster that runs 3,000 pods. That we believe that, well, it will get better by the end of the year, because we are currently working on the features, not the performance, but we will move to increasing those numbers just after the launch. We also have a Google Container Engine, which is really simple, which basically manages the master for you, so the API servers, schedulers, whatever. It runs the same open source system that it's open, but we manage the machine that actually runs all those stuff for you. So you want everything that you do, just send the request please run those pods somewhere, and it will just run it on your machines. And also 2 days back it went to beta, so it's kind of reddish. The important thing about Kubernetes is that it's not a Google project anymore, not only Google project. We have a lot of contributors from Red Hat. Red Hat contributes a lot to our code base, which is as I said, open source GitHub. We have nearly 400 contributors, but all the owners are from Google or Red Hat. So we also share the ownership. I think we also have some owners from CoreOS. We have really good relationship with CoreOS. Which is important for us also because they wrote the HCD. So if we have good relationship, so if we need some features from HCD, it's easier to make them actually work on it. Probably most of you heard about Mesos. So Mesos also noticed that Kubernetes is a nice thing to use. So they introduced Kubernetes as a scheduler on top of Mesos in the Mesosphere. And a lot more. You can go to the GitHub and see what's going on. The question we get asked a lot, why we do this? Well, basically we believe that once we reach, we will have a standard, and all the workload will be portable, so you can just take everything that you run on whatever AWS and run on your own cluster, or move to our cloud or Microsoft or whatever. Everyone will benefit. We strongly believe in workload workload portability. That is probably the most important thing for the community right now. Plus, we believe that we have some experience that's unique for us in running containers in scale, and we want to share them with the community. Yeah, it's also nice that actually this container thing is closely related to the microservice architecture, which is kind of like a new sexy right now, or was new sexy some time ago. Yep, and that's pretty much it I have to tell you today. So if you're interested, please look into our GitHub repository, and if you want to help, just you can contribute whatever you want. Thank you.